In this video, we'll discuss diagonalization. We're told that the eigenvalues of the matrix A are 2 and 4. The problem is to find a matrix P that diagonalizes A. We can start by finding a basis for each eigenspace. Let's look at the first eigenspace, E2. To investigate that, we'll set up the system A minus lambda I. In this case, lambda is 2, so we'll write A minus 2I for the coefficients, and that's a homogeneous system. Setting up this system, we're effectively just going to be subtracting 2's from the diagonal entries of A. So let's do that subtraction first, and all the other entries are going to remain the same. Now our goal will be to put this matrix into our REF. So we've already got a 1 in the upper left here. Let's do row 2 minus 3 times our pivot row, and at the same time we can go row 3 minus our pivot row. Moving down and to the right, this 2 is going to be our next pivot, so let's take row 2 divided by 2. And now we've got our REF. So let's go about solving this system. What we're finding are eigenvectors. Normally they're called x. So let's call our variables x1, x2, x3. And taking a look at the leading ones, we've got leading ones in the first row as well as in the second row. There's just a single column here without a leading one in it. And that tells us that x3 is going to take on a parameter value. So let's say x3 is equal to t. Top row tells us that x1 plus x3 is equal to 0, meaning x1 is equal to negative x3. In other words, x1 is equal to negative t. Second row says that x2 minus 3x3 is equal to 0, meaning x2 is equal to 3x3. In other words, x2 is equal to 3t. This tells us that a type of eigenvectors x that we can have will look like negative t, 3t, t, or if we write that a little bit more concisely, they would look like negative 1, 3, 1 times t. So in other words, any non-zero multiple of this vector minus 1, 3, 1 would be acting as a basis vector for this eigenspace. So let's record our basis over on the side here. There are two natural choices here. You could choose this vector minus 1, 3, 1 here as your basis vector, although when the first component is negative, we typically multiply the entire vector through by negative 1. So choosing 1, negative 3, negative 1 would probably be the best choice here. I've just recopied the original matrix A, the two eigenvalues that we were given, as well as the basis for E2 that we found on our previous screen. So remember we said one possible choice of a basis for E2 was the vector 1, negative 3, negative 1, although any non-zero multiple of this vector would also be a correct choice. Let's take a look at the eigenspace E4. We'll be setting up the coefficient matrix A minus 4I, and it's a homogeneous system. So we'll look back at A and we'll subtract 4 from the diagonal entries. And we're going to put this matrix into our REF. So let's start by taking row 1 divided by negative 1. Just change the signs all the way across there. Next, we can take row 2 minus 3 times our pivot row, and we can also do row 3 minus our pivot row. And there we have our REF. Now there's only one leading one in the first row here. That leaves us with two columns without leading ones. And let's name our variables x1, x2, x3 here. So both x2 and x3 are going to take on different parameters. Let's say x2 is equal to s and x3 is equal to t. Top row tells us that x1 minus x3 is equal to 0. In other words, x1 equals x3, which is equal to t. So if we write up our vectors x, we're describing the type of eigenvectors that we can get corresponding to this eigenvalue here. They will have the form TST, or if we write that in vector form, that would look like 0, 1, 0 times s plus 1, 0, 1 times t. So at this point we can pick out our basis vectors. A basis for E4 consists of this vector together with this vector here. So 0, 1, 0, 1, 0, 1. We're almost done. We found a basis for E2 earlier in the problem. We've now found a basis for our second eigenspace, E4. Putting these things together, the matrix P that will diagonalize A just has these basis vectors in its columns. So let's say the first column looks like 1, negative 3, negative 1. Following that, we've got 0, 1, 0, and then 1, 0, 1. Now, it's important to mention that there is more than one correct choice for the matrix P. For instance, you may have had your columns written out in a different order. That's fine. And you may have made slightly different choices for the basis vectors at various points in the problem. As long as you did all those calculations correctly, that would be a valid alternate answer.